Welcome back. Today we're going to be working on solving logarithmic equations. But before we do, I want to do a couple reminders because in order to solve, we got to kind of reflect on some of our properties we've talked about so far this unit. To start with, I want you to remember that log base b of x, if that's equal to log base b of y, then we know for sure that x is equal to y. Okay, this is called our equality property that we went over in the previous lesson. With this in mind, we can solve problems. If we have log base 10 of x, and that's equal to log base 10 of 14, then the only thing x can be is 14. So that's kind of the general idea today. Now there's a couple more wrinkles we need to, illustrate for you guys, but that's essentially what we're covering today is the equality property. Next, I want to remind you of an important detail about, undoing a squared. So if you have x squared equals 16 and you undo that with its inverse operation, so the inverse operation of squaring something is square root, what the result is both the positive and the negative version of the square root of 16, which is 4. If you think about plugging both 4 and negative 4 in for x, both will equal 16. And we can kind of extrapolate on this idea, and we can kind of think of this as like anytime we have, any even numbered exponent we're getting rid of. So in this case, like we have x to the fourth. If we want to undo that, we could raise both sides of the 1/4 power or the fourth root. So what results is kind of x is equal to both plus or minus the fourth root of 81, which is 3. But we do need to remember that because it's going to impact us today. Another reminder, below here we have 2 to the x power is equal to negative 4. What that result is, or what that logarithmic form is log base 2 of negative 4 is equal to x. Just to remind you guys, the argument and the base of a logarithm, they cannot be negative. You can't have a negative base and you can't have a negative argument. So, example 1, example 2, what we're looking at here is we're looking at, two logarithms that have the same base that are equal to one another. So what we can state, because they're both log base 9, we can confidently say that our arguments are equal to one another. So some students like to think of this as like the log base 9s cancel out. Really we're able to say that not because they cancel out, but because the arguments are equal to each other if the base is the same thing. And then from here, you can kind of solve like a normal, algebra problem. So we're going to subtract 4x from both sides. We've got negative 3 is equal to 6x minus 15. We're going to add 15 to both sides. So I think we end up getting 12 is equal to 6x. So then if I divide both sides by 6, end up with x is equal to 2. However, in these logarithmic problems, when we are solving, remember we stated that our argument, which in this case is 4x minus 3, it has to be bigger than 0. So at the end of these problems, you do need to take both of your arguments, or how many arguments you have, and you need to check to make sure your answer for x isn't going to make that argument negative. So the way I do that is I set up two little inequalities that I've done in blue for you. I'm going to solve those. I'm going to make sure that it's a true statement. So on the left here, if I add 3 to both sides, then divide by 4, I get x is greater than 3/4. So is my x of 2 greater than 3/4? I believe 2 is bigger than 3/4, so we're good there. On the right here, I'm going to add 15 to both sides. I've got 10x is greater than 15. Divide both sides by 10. Is x greater than 1.5? Well, 2 is also greater than 1.5. So with that, checking our work in mind, checking to make sure that our arguments don't turn negative, we have found that our answer is in fact 2. Next up, we've got log base 5 of 2 plus log base 5 of x plus 5 is equal to log base 5 of 6x. So before I start this problem, what I'm going to do is I'm actually going to condense the left-hand side of this equation by using my product of logs property. So I'm going to turn log base 5 of 2 plus log base 5 of x plus 5 into log base 5 of the multiplication of my arguments, so 2 times x plus 5. Now I can use that equality property. Now I can say, hey, I've got log base 5, 1 on each side. So now I can just equate my arguments. So I've got 2 times x plus 5, which is equal to 6x, do some simple solving here. So I've got 2x plus 10 is equal to 6x. Subtract 2x from both sides. 10 is equal to 4x. Divide both sides by 4. So I end up getting 10/4 is equal to x. Of course, we're going to simplify. So we end up getting 5/2, or 2.5 is equal to x. However, we do need to double check to make sure that, my argument, x plus 5, won't turn negative with an input that is, 5/2. So what I'm going to do is I'm going to take x plus 5. I'm going to set it greater than 0. And I'm just going to make sure, is my answer 5/2 greater than -5? It is. So we're good there. And then my other argument, which is 6x, I'm going to set that greater than 0. Divide both sides by 6. So in this case, my, x value's got to be bigger than 0, which it is. So we're good. So we do need to check our work on these solving logarithm problems. Otherwise, you could potentially get an answer that's undefined. Another situation that might pop up is one where the base is missing. And with your base missing, you got to be a little careful, because just remember, guys, that base and that argument, they can't be negative. So let's solve this by just making this into, x squared is equal to 9. Okay. So x squared is equal to 9, just because I, turned it from logarithmic form to exponential form. So if I square root both sides, I got to remember, I got to account for both my positive and my negative square root of 9, okay, which is 3. So I've got both, a positive 3 and I've got a negative 3. However, I need to keep in mind, because this, because this base has to be bigger than 0, that negative 3 is what we call an extraneous solution. It's a solution that popped up with our algebraic process, but doesn't actually satisfy for what x is. So the only solution to this problem would be x equals 3. All right, so in this next example, we're going to do that same thing. We're going to solve for, x. So we're going to turn this into exponential form. So I've got 4 to the second power is equal to x plus 9. I've got 16 is equal to x plus 9. And then I'm going to subtract 9 from both sides. And what I get is 7 is equal to x. So, per usual, I'm going to check to make sure my argument of x plus 9, make sure x does work. So if I subtract 9 from both sides, x has to be bigger than -9, which, last time I checked, 7 is bigger than -9. So we are all good for this problem. So difficulty can ramp up a little bit when you have a situation like this where you have to, multiply together your arguments because of the product property of logarithms, and what results is potentially some extraneous solutions. So let's go through it. So same thing, we want a single and a same base logarithm on both sides. So I'm going to combine this left side of this equation by multiplying together my arguments. So I've got x minus 3 times x plus 5. What I notice now is that my logarithm is a single logarithm on both sides. It's also got the same base, so I can equate my arguments. So I've got x minus 3 times x plus 5 is equal to 9. Now I got to solve for x. So I'm going to FOIL this. So x times x is x squared. Negative 3 times x is negative 3x. 5 times x is 5x. Negative 3 times 5 is negative 15. That's equal to 9. Do a quick simplifying step by combining like terms on the left-hand side. Negative 3x plus 5x is positive 2x. Now I'm going to subtract 9 from both sides. So I get x squared plus 2x minus 24 is equal to 0. So unfortunately in this case, I do need to factor this in order to find out what x is. So I'm thinking of two numbers that multiply together to give me negative 24, add together to give me positive 6 or positive 2. I think my two factors are going to be positive 6 and negative 4. So kind of running out of room here, so I'm going to go up to the right. So what I kind of know then is that x plus 6 is equal to 0, or x minus 4 is equal to 0. Using that zero product property, I'm able to quickly solve for my two solutions, which right now look like our x equals negative 6 and x equals 4. But I do need to check where my extraneous solutions could be. So I've got to set x minus 3 greater than 0, so x has to be bigger than 3. And also, x plus 5 is greater than 0, so x has to be bigger than negative 5. So in this case, that x equals -6 answer is what we call an extraneous solution. So I cross it out, I write the word extraneous, and then I circle my one and only one answer, which is x equals 4.